new chapter starting from this lecture. And title of this lecture is source coupled converters and infilter interaction. In the previous chapter, we went through all the details about the dynamics of load coupled converter, and we switched our attention to this topic, source coupled converters. So we'll be dealing with the dynamics of converter coupled with an arbitrary source subsystem. But the simplest form of this source coupled converters is this infilter connected converter. Infilter is the simplest possible configuration of source subsystem. So first we'll focus on that. That is actually, we'll be dealing with this infilter interaction between infilter and converters, downstream converter. This topic is very old, and this topic is very classical, and there are some information about this. Most work is done by Dr. Middlebrook. Right? So we'll be dealing with this. Infilter coupled converters. So the converter is connected with infilter at its input port, and there are some interaction between infilter dynamics and converter dynamics. They call it infilter interaction. So this is the simplest form of source subsystem interaction with downstream converter. So let me sketch this. First, I'd like to address why we need infilter. Many people, they just ignore it. Okay? They won't pay attention on this, but that's not the correct approach. So this infilter is very important. Suppose you have this kind of situation. Here is your converter, right? Maybe buck converter is the worst case. So buck converter is located here. Buck converter. And of course, you need some filter here. For the same reason, this converter need filter stage in front of it. For the same reason, there should be another filter. We call it line filter. This one is the in filter, and there is another power stage coming in. Oh, let me. Okay, maybe some converter is here. All right, and you should have filter stage. This is ideal voltage source, so this is called in filter, and this is called line filter. Of course, this thing will appear here again in parallel with the first one. So you have this kind of situation. All right. This is the the distributed power subsystems. Distributed power systems we are talking about. Okay. So now we are focusing on this. All right. I'll explain why this stage is needed, why that infilter is necessary, why people bother with this, and why people suffer from this. Suppose this is the buck converter, then maybe, for example, the input current of this buck converter is this pulsating waveforms, and maybe the average value of this can be considered 5 volt, 5 amp, 5 amp, all right? Then fundamental component of this thing at this frequency, at this switching frequency, not line frequency, this can be 10 kilohertz, something like that. And first, the fundamental component of this is around 1 amp in general. It depends on the duty ratio of this converter, and usually maybe the 1/5 of this average value. Yeah, will be the first component, and the requirement of this is this fundamental component of the current coming from this input side should be very small. Like I read some books about this specification, and specifications are very complex. So I cannot figure that out, the exact requirement. But fortunately, there was one book, okay, that the Fundamentals of Power Electronics, written by Erickson, Bob Erickson. He said that usually this one, 0.1, no, the current of this sinusoid component magnitude is around 0.1 milliamp. So this 1 amp is going in, and that should be attenuated by this much, which is, this is 10 to minus 4, right? So it requires 80 dB attenuation at, for example, this one. So this is a huge requirement, okay? So designing of this thing is not easy because this attenuation requirement is so large, right? So this is the requirement. You should obey this. They enforce this by the law, okay? So all the industry people should satisfy this, okay? So they struggled for a long time, and somehow they find out the way of designing this, okay? Then there are another problem was coming up. That is the problem of interaction between this filter stage and the buck converter downstream. This converter was originally very stable with ideal voltage source. Then as soon as they connect this in filter, then they see some oscillation going on. Okay, that was the beginning of studying this problem, interaction between this filter stage and downstream converter. They call it in-filter interaction. The guy first investigated this problem is Dr. Middlebrook, and he published the very famous paper, glorious paper, in 1972. Okay, long time ago, maybe 50, half a century ago. All right, that is the beginning of this story, and that is the beginning of study about the interaction in DC power distribution system. The basic problem of this thing is this buck converter is presenting negative incremental resistance. That was the problem. Okay, if you connect this filter with -1, you are building a oscillator. That happens a lot in the past, and people they suffered. And Middlebrook, he documented the remedy of this problem in the paper form. In the paper form, that paper is extremely useful. That is just regular conference paper. Okay, so but all the people, including myself, they refer that paper when we are talking about this kind of business, right? So in that paper, he first defined the term minor loop gain. Actually, so we'll go through the details about this. So I'd like to emphasize this. This is the inherent problem with any DC to DC converter. If you design, fabricate DC to DC converter, you should attach in-filter all the time. Of course, in your lab, you can skip this, but that is your own business. If you work with other people, okay, for example, the DC grid system, then you should add this, and for the same reason, you should add this, right? So problem with this interaction between this stage and this stage is called in-filter interaction, right? And you have the same problem here. At this interface, this problem is much more complicated than this one, because this source system is connection of everything. So you have more complex problem. But the way of solving this problem remains the same. So if you understand the problem of this in-filter interaction, then you can easily extend the analysis result to this to solve this general problem. That is our approach taken here. All right. So even though the title of the chapter is source subsystem interaction, we will be talking about this in-filter interaction for 95% of this technical content. And later on, finally, I will have some short but very important comment on the extending the result to the general load subsystem. Right? And the way presenting this is also important. So it's very good idea for this. Using 3 different and distinct cases, like some case study type presentation, right? So we have 3 cases will be discussed soon, and finally we'll have some conclusion how to extend the result of this analysis to the source coupled converters. Not only this one, but also the other one in the complicated structure, right? So why we have only 3 examples? So due to the nature of this interaction, the interaction problem can be classified into 3 cases. One is converter with voltage mode control. Okay, so when the voltage mode control is applied, then result of the analysis for the buck converter and boost converter and the buck boost converter, they are all the same. Okay, so we take boost converter as an example, but the result can be applied any converters, any PWM converters, as long as it employs the voltage mode control. Okay, but for the case of current mode control, you have quite different situation. For the current mode control, it boost converter and buck boost converter, they are the similar, almost the same. The analysis method and result are the same, but this buck converter is very different, extremely different. So you have 3 cases. So this can be considered as the case study for the older PWM converters with the voltage mode control, and this can be considered as the analysis of PWM converters other than buck converter with current mode control, and last one is this buck converter with current mode control. Okay, they are different, very different. All right, so this might be, then the result can be easily extended to the source coupled converters. Okay, to apply the result for this type of converter. Okay. Basically, they are the same. Right? We are talking about the source impedance seen by here and interaction between source impedance and input impedance of this converter or this converter. All right. Again, this is the architecture of conventional DC power distribution systems. We have these converters, all they are connected in this manner. This filter stage called in filter, and this filter stage called line filter. So we will be talking about the interaction problems at this interface, but result will be extended at any interface existing in the system, right? To analyze the interaction at this interface, we use the load coupled converter. That topic was covered thoroughly in chapter 10, right? Okay, so the same concept, uncoupled converter is important. Okay, otherwise there is no way of designing the control of this each individual converter. So we adapted the concept of uncoupled converter. And good news of this is the conventional design procedure developed for resistive load, which appears all the standard textbook, is still applicable to this uncoupled converter. That's very good news. Finally, you use Middlebrooks extra element theorem to evaluate the performance of converters in this real operational situation. Load coupled converter, load coupled case, and source coupled converters, source coupled cases. Okay, so this is the key thing, extra element theorem. All these business is related with Dr. Middlebrooks' work, basically. This is 2-stage power distribution system, we'll use this system. Actually, we used this system in chapter 10 to address the load interaction. Right? So we use the same system, and now we include this. So this can be considered. This is the infilter. So infilter is located here. But this system is complicated. All right. So we simplify this. This is simplified to this simple diagram. So it's the same thing. Okay, upstream converter here, downstream converter is there, and line filter stage and infilter stage. Okay, here. It's called the Source subsystem, but this is the simplest possible structure of Source subsystem. This is just one simple filter stage combined with ideal voltage source. We further simplify this. Okay, this is the same diagram. And we further simplify this. This is all of this part, load subsystem, is simplified to this ideal current sink. So this is a rather dramatic simplification, but finally, fortunately, this GIU, the input impedance of this converter, is not sensitive actual characteristic of this load, okay, this subsystem, all right? So instead of using this, you can just replace this with this current sink. So at this point, this is uncoupled converter. The reason for this is this dynamics of this GL is almost independent to this, not presenting any significant impact on this GIU. In other words, this GIU characteristic is almost independent of this load impedance characteristics. So why we bother with this? So we just replace with the current sink. The result will remain the same. So this is the final result, final model we will be dealing with. All right. Another simplification. This is very simple structure of a single stage LC filter. There are two reactance components. This one is inductor. This one is capacitor. The inductive impedance should appear here. Right? The purpose of this is this G1 branch should present very low impedance to low frequency component, particularly for DC component. This present very small resistance. Right? So this gotta be this inductive series network. And you need this capacitive, this parallel network. High frequency component of this input current should circulate through this. Without going through this, this should present very low impedance, reactance at high frequencies. So you need capacitor. If you change location of this and this, it don't work at all. Okay? So this structure is required. And another thing is, you employed this inductor, you applied capacitor here, then you are expecting the current attenuation of minus 40 dB per decade. Because you employed two reactive components, each of them will provide 20 dB attenuation, and you have another 20 dB attenuation, then they will provide 40 dB attenuation at high frequency, something like this. Okay, so this should be this attenuation, but it is impossible for this structure. By putting something here, you create a zero. If you have zero at this frequency, this zero is called the ESR zero. With the ESR zero, this high frequency slope becomes minus 20 dB per decade, which is very, very bad news, right? So you need a very large reactive component. So to avoid this situation, basically we are using two reactive components. Then you should have this minus 40 dB decade slope at high frequency. Okay, to achieve that, there is some variation of this structure. Okay, this is the worst case. Okay, this is not practical, but I use this. This can be used for some case. And the theory developed with this simplified structure can be applied to all the other structure of low-pass filter. For example, there are something like this. Okay, this or this, and okay, they are all single stage filter. We have 3 reactive components here, but one of them is very small compared to the other one. So with this single stage configuration, this type of filter provide this attenuation. But we have some price to pay. This resistor can dissipate the DC power, and sometimes this additional inductor we include can be very large. And this additional capacitor we include can be very large. So that is the price you should pay. But our purpose is, with this structure, we want to have this minus 40 dB attenuation at high frequencies. Okay? But still we will be using this, right, to simplify the analysis. Again, as I said, all the discussions we are doing here can be applied with this practical structure with minor modification. If you need more attenuation, you attach another stage of this, but design will be complicated. But there are some way of selecting the component for the optimal performance of this thing, right? But in the past, they just focused on the attenuation, voltage attenuation from here to there, or current attenuation from here to there. Okay, so this is the story. So you have this structure, and this will be simplified this. You use the Thevenin's theorem, and this is the G1, and this is the G2. Then this one, output impedance of this filter with input port shorted. We use notation of this GOF0. It's just a parallel combination of this. This part is shorted. Okay. So this is the source impedance, right? And this is the Thevenin's voltage. This Vs is divided by impedance, right? So this is the impedance ratio, and this is then you should replace this voltage with this. Okay, so this is basically Thevenin's form. Okay, and another thing I'd like explain to you is this very important and very simple characteristics of this passive network. Of course, this filter is built only using the passive component LC and resistor. For that case, we have this feature. Okay, this is V1 plus minus, V2 plus minus. So first one is AVF, is the voltage attenuation. AVF or AUF, AVF is attenuation of this voltage. So V1 is input and V2 is output. When evaluating this, okay, this is I1 and this is I2. Okay, so direction can be changed. This I2 direction can be changed, but somehow we use this, right? Then when evaluating this, I2 should be 0. That means output is open, all right? So evaluate this ratio with I2 is 0. Okay, and another very important attenuation is, this is our case. Right? This current it goes to the DC to DC converter. So there is a pulsating current. So it has DC component and AC component. What you want is DC component is only coming from this port, and AC component is circulating with this converter. For that purpose, we define current attenuation like this. I2, I1, okay? I2 is input and I1 is output. And when evaluating this, V1 gotta be 0, okay? All right? So when evaluating attenuation from this voltage to this voltage, output port should be open, right? When evaluating the current attenuation between this and this should be shorted. Then with this, you have this relationship. AVF is AIF. They are the same all the time. This property is called the reciprocity property. Right? So this indicates this forward voltage gain with output port open is the same as the reverse current gain with input port shorted. This is true for all the passive circuit components because the reason for this is, maybe you remember this, this is a two-port network. Then there are a bunch of parameters defined, G parameter like this, G21, G22. Then another set of parameter, H parameter, Y parameter, G parameter, A, B, C, D parameter. All of these parameters, this off-diagonal element is always the same. Okay? Maybe you remember this. Expression of this, expression this is the same. Okay? This is the fundamental nature of linear passive network. So because all the line filters, in filters, I'm talking about the conventional line filters and in filters, we fabricated them with this passive component. So this is always true. Right? For one example, AUF is voltage attenuation, define this. Then this is what? This is the impedance. Okay? Sum of two impedances. You have G1 here and G2 here. Then denominator is this and numerator is this. Okay? Right? But you modify this in this manner. So this is G2, G1, then multiply numerator and the denominator with G1. Okay? Then you combine this. This is what? This is the output impedance. This is GS. Okay? So this is GS. GS is GOF0 divided by G1. Right? But this is much easier to evaluate because during this filter analysis, this always comes out. And again, somehow you need to evaluate the G1. Then the division in the log scale becomes subtraction in the dB scale. Right? So you can construct this graphically very easily. If you have very complicated structure, it's not easy to derive this directly. But this thing always works. Okay? This is the first. Then maybe you define this. AIF is I2 in the downstairs, I1 in the upstairs with V1 equals 0. Okay, so I2 is going like this. Then the component of the I2 coming from this branch is, you know this, right? This is G1 plus G2. And here you have term G2, which is the same. Right? So this one becomes same, this one becomes same. Then this can be represented by the same expression. So always this forward voltage gain and the reverse current gain, they are the same. Okay? That is the one important thing to know. And it will simplify a lot when you are dealing with some tricky circuit diagram, circuit structure for the line filter or in filter. But our interest is not current attenuation or voltage attenuation. Okay, so we forget about this problem. This can be dealt with other guys specializing the EMI things. Okay, So our attention is dynamic interaction between infilter and this downstream converter is called infilter interaction. Again, by this guy, Dr. Middlebrook. Strange name. Huh? Brook is the small strip. In the middle of something, there is some small strip. That's his name, Middlebrook. Okay, and this is the diagram of uncoupled converter. So this part is showed it, and we defined this GIU and the GOU and the loop gain. Okay, so as this DC converter, we are only interested in these three transfer functions. Maybe some people, they define transfer function from the reference voltage to out voltage. That definition is meaningless. Nobody will change the reference voltage. Reference voltage is fixed at DC all the time. Okay, so there is no meaning of transfer function between reference voltage and from reference voltage and out voltage. Does not carry any significant implication on this because this reference voltage always is fixed. So we are only interested in these three things. Output impedance, loop gain is directly related with the stability of this converter, and this GIU is related with interaction coming from this source system side. So now you have this is an infilter coupled converter, and GOF0, which is just a parallel combination of two impedances, series impedance element and parallel impedance element is called source impedance. So you have this problem and this GO0 and this one AUS attenuation from here to there, and this output impedance loop gain, and this impedance this impedance remain the same. Is there only our interest, and we went through this in chapter 9. Okay, chapter 9. Refer to content of the chapter 9 or chapter 1 in your book. Chapter 9 in the original book. Okay, so this is audio susceptibility. All right. But this, okay, that's fine. So this is the source impedance, which is GO0, GOF. It's not true. Should be GOF0. Okay, I think your book is correct, right? And this one, this is the input impedance of this closed loop controlled downstream converter, and this is the input impedance seen here with feedback loop is open. Okay, so it's open and output is shorted. Okay, very strange condition. That condition is coming from the definition of the ET. You remember the definition of the null driving point impedance and the regular driving point impedance. So null driving point impedance, we assume the output of transfer function is 0. And in the null driving point, regular driving point impedance, we assume the input of transfer function is 0. Okay, with that requirement, so we need this, and we have this regular closed loop input impedance. Here we have this. This is output nullified input impedance, and this is open loop input impedance. Okay, so we need 4 input impedance. So this is the special case. Previously, in this case, let me delete this. This one is not good. Okay. So for the load interaction, load side interaction, we considered this. This is converter connected with ideal voltage source, and the source subsystem is considered as this pure ideal voltage source. And we follow this one is followed by this single stage filter. For the simplicity of discussions, we assume single stage, but it can be any low pass filter. And you have control loop here to regulate the out voltage, and we defined GL, load impedance, GL, and we need this one, okay? And we need another one, GOU prime. GOU is output impedance with this input port shorted. GOU prime is output impedance of converter with input port open. So here we need two impedance of upstream converter, but here we should use four different input impedance of this converter, okay, defined in the specific condition. So it complicates our analysis, and I repeated the definition of those impedances. So you have four different input impedance with distinct definition. Okay, this is the closed loop input impedance. This is regular input impedance, and GI prime is open loop. Loop is open, and output is shorted. Right, that is the GI prime, and GI prime is output nullified, but still feedback loop is closed. Okay, so this feedback loop should be closed to have output nullified condition. All right, so maybe it's better to put here closed loop output nullified input impedance of converter, and this is IGI triple prime is open loop, just open loop. And previously GI single prime was open loop and output is shorted. Okay, so we need four transfer functions here. This one. So two of them are closed loop. Closed loop transfer functions. Two of them are open loop transfer functions. All right. Okay. Then let's take a look at the impact of these things. So this is the typical example of asymptotic plot of magnitude of four different input impedance we identified in the previous slide. GIU, GI prime, GI double prime, and the GI triple prime. So we need four different input impedances compared with this GOF0 is source impedance. So shown here, okay? GOF0 is source impedance, which is drawn this purple, thick purple line, okay? And this GIU, GI prime, double prime, triple prime. This is GIU, is shown here, and GI double prime is here. They are the closed loop input impedance. Thing is, closed loop impedance, low frequency magnitude is very large, and they are the same. Okay, and actually this value, we know this value, right? So this becomes a part of input impedance of this converter. This low frequency part of this represents the incremental resistance. So this value of this is 20 log VS divided by IS. Okay. So VS is DC value of this, and IS is again DC value of this. Okay. Maybe it has some ripple component, AC component, but we are talking about the average DC value. I don't know, RMS or whatever, but average value of this is shown here. Okay. So two of closed loop impedance. This one has these characteristics, and this impedance has minus incremental resistance at low frequencies. The other two open loop transfer functions is shown here, GI prime, GI triple prime. Okay? They are very low in magnitude. Okay? So for the typical case, this is GOF0, is they usually overlap with this one. At this region, this GOF0 and GI triple prime overlap this much. And for this region, this GOF0 and GI prime overlap this much. It affects the closed loop performance of the system. For the stability, if there is a gap between this and these two curves, the system remains stable. I will prove that, but this system is stable. The closed loop performance is affected this much. All right. So usually this will deteriorate the performance of downstream converter, and because of that, this in-filter interaction is always something dangerous and something harmful for the downstream converter. That is true. But that is not the true for the load subsystem interaction. It proved that, okay? Sometimes the load interaction will destabilize, it will stabilize previously unstable upstream converter. All right, that can happen. But in this case, this in-filter interaction is something detrimental all the way, all the time. And expression of this is 4 impedances is shown here. Okay. Oh, I'm sorry. This one. So we didn't go through all the details about this, but all the derivation is provided in chapter 9. It's not easy. No, it's not difficult. You can easily follow this. Again, there are so many terms, different input impedance with different operational condition is due to the definition of null driving point impedance and the regular driving point impedance. That condition will be changed by this original transfer function, right? The input of this transfer function and the input of this function is very different. Because of that, you have different definition for this 4 different cases. Okay, let me go back to here. Okay, first one. This one is not good. This one is not good, right? The original equation for this audio susceptibility with source impedance is AUF is attenuation of in-filter stage, AUF. So this is a transfer function of filter stage times audio susceptibility of uncoupled converter. So that is A U and numerator is just 1 and denominator is 1 plus GOF0 divided by GIU. Okay? So for this case, we have this huge separation. Not huge. We have some separation between this GIU, which is this, and this GOF0. So this denominator is gone. So this denominator, this one is gone. So the result is this. So only we have this. Then this is the addition of 2 transfer functions in dB scale, right? So we have for the attenuation, this is the negative. This is the attenuation, is negative. We are adding them. Then we have subtracting more. We have something similar to this, right? So this is the result of the in-filter, which is obvious because we have filter stage in front of this uncoupled converter, and with this condition, this term becomes 0. Then we have more attenuation. So this part is attenuation of this downstream converter, and this part is attenuation of what? Line filter, no, in-filter, right? So that is very easy. And this one, loop gain is original expression for the loop gain is TMS is TMU and GOF0. Oh, we have 1 plus here. Always we have this form. 0 and gi prime 1 plus gi double prime go f0 divided by gi triple prime. Okay, so based on this thing becomes very small, right? So gi double prime is somewhere here. This is the way below from this. So this can be ignored compared to 1. So numerator is just 1. But this one, we are comparing this GOF0 and this GI triple prime, which is this red one. All right. So this will appear in the transfer functions, but it appears in the denominator. So is the final form is something similar to this. This is a linear scale. This is a log scale. This becomes positive, but it comes in the denominator. The original one was this is TMU. Then TMS. In TMS, you have subtraction of previous area. This area, you have this, right? So this blue curve is loop gain of source coupled converter, and this is the magnitude curve, and below one is the phase curve. Somehow you have this kind of characteristics. And for this output impedance, original equation is this GOU GIU, right? So this one can be ignored. Okay? Because of this characteristics, comparing the magnitude, the denominator can be ignored, but this numerator remains effective. Then this is okay, just ignore this. And this is the multiplication in linear scale, which is addition in the log scale, dB scale. So you have some boost here. Output impedance will be boosted at this region, okay, this region. So you are seeing the impact of this numerator term at the low frequencies. Okay, and the final comment on this is the intrinsic case for the voltage mode control. All right. So for the voltage mode control, you optimally designed your converter and you optimally designed your infilter, then always you have this kind of situation, regardless of converter topology. Okay, so you are using boost converter with voltage mode control. That is very unusual. Okay, it is usually known that the voltage mode control is not adaptable to boost or buck converter. So voltage mode control is only good for the buck converter. But I'm using boost converter example to address the nature of these things. This is most pronounced for the boost converter case. But if you change the topology, you will have almost the same conclusion, same shape, all the impedances and the source impedance. Okay, so this can be considered general analysis. All right. Okay. So the performance will be changed like this. We'll go through this again in every detail, right? So we'll approach this with some analytical way, graphical way, and we further evaluate the performance of infilter coupled boost converter later. So this can be considered just the introduction, showing that impact of infilter on the converter performance. Okay, so first one, that is the first one. Second one is how about stability? Suppose this converter was stable this uncoupled converter was very stable. Then you attach this with line filter. Then how about the stability of entire converter? Is the biggest concern. We did similar analysis for the load coupled converter, and our conclusion was if load coupled converter, this is the ideal voltage source, coupled with line filter and converter, then it is almost impossible to make this converter unstable. That is the case. But in here, the opposite is true. This converter can be very easily become unstable. Okay, so we'll go through that. Okay, so we need, this is the expression of loop gain of in-filter coupled converter. We went through this in the previous slide. So this is the case. Then characteristic equation of any system is 1 plus loop gain equals to 0, which is this. Okay, so this is the expression you need to evaluate, and this expression is written in this manner. So you multiplied this one here and here, then you have this. All right? This looks very complicated. This is very intimidating. You have many things, GI double prime, GI triple prime, and the G. Okay, so it's very complicated. Okay, I thought this is very complex. So somehow my student, one guy, he is Indian student, he was doing something. And finally he find out this, factorizing this thing. Right? Conclusion is very easy, but this procedure was not easy, probably. I tried this many times and I just gave up. It's so complicated, but somehow he managed this equation in this form. So this is A is repeated here, and this one can be factorized like this. All right? So validity of this equation is if we multiply this here and multiply this here, this one cancel, multiply here, this one cancel, then you have this original expression. All right? So obviously it's the same equation. Okay? It looks further complicated. All right? And this is, I think it's better to label this A and B, and this is B. Okay? This is B. Same thing. Then you take out this. You have GOF infinity and GOF infinity. Take this out here. All right? Then you have this term. You are seeing this term is here. Okay? And this term is very familiar to us. We derived the input impedance of converter using the feedback theorem in chapter 9. All right? The result was this. This term in here with this blue underline is simply this input impedance of closed controlled converter. All right? This whole thing can be simplified to this. This is derived in chapter 9. All right? So you are going through all the details from the definition of this loop gain of source coupled converter, and it beautifully written in this manner, and this will be replaced this. This means what? This is the loop gain characteristic of this system. It just you have two terms, factorized terms. One is 1 plus TMU, and this one is GOF0 divided by GIU. Okay, this is the impedance ratio at this point. All right. So then we defined 4 different input impedance for this converter, but in this stability analysis, we only need this one term. All right, and this term is called, in his original paper, Dr. Brook, he named this as the minor loop gain. Okay. So we have the similar situation in load coupled converter. At that time it was GOU, this one is GL, and we also named this term as the minor loop gain. Okay? The original definition of minor loop gain comes from this in-filter interaction analysis. The implication of this equation is the same as the previous one. The root or eigenvalues of this characteristic equation is union of root of this thing equals to 0 and the root of this term equals to 0. Okay? That means by connecting this, you have original the eigenvalues for this uncoupled converter, and you have some additional eigenvalues. That eigenvalue is generated by this equation, right? So if this converter is originally stable, then if this term equals 0, this the Nyquist stability criterion, then system remains stable. Okay? It's the same conclusion as the previous case, right? So same rule applies this source coupled converter and load coupled converter, which is very, very amazing. Okay? So, and the order of this one, this GOU is coming in the second floor, and the GIU is coming in the first floor. Previously, you have GOU. This one is coming in the second floor, second stair, and this one. This was GL, right? So the guy coming later goes downstairs, okay? Coming in front comes upstairs. Same order, right? Then remaining story is the same as the previous case. So we started from this equation, and this equation is factorized by these two terms, okay? So solution of this one, so eigenvalues of this composite system is sum of eigenvalues of converter and the sum of eigenvalues coming from this term, or root of characteristic of this load source coupled converter is a union of root of this one, this uncoupled converter, plus this one. Okay? So this guy is stable. Then we just take a look at this. All right? So you plot the polar plot of this one, GOF divided by GIU, which is defined, this is originally defined as minor loop gain. Okay. Let me just show this. So you know this, okay? No. Suppose you have this simple single stage filter, then this analysis involved with this one, input impedance of filter with output open, and output impedance of converter filter with input short, and maybe another one is needed. So this is the output impedance of this filter with infilter, input open, and downstream converter. So notation of this GIC is not good. The same GIC is same as GIU, almost the same as GIU. So you have this, okay? And this impedance is, let's define this G1. Let's define as G2. Then G1 is this. The G1 is this one. Originally G1 is this one. Okay. This is a series connection of this filter and ESR of this inductor. And the G2 is a series connection of capacitor and the ESR of that. So this is G2, right? Then input impedance of this filter is just the series connection of this G1 and G2, not GS, G2. This is G1, right? Then series connection of this. So you just take the larger asymptote for all the frequency. Then this is the GI infinity. And you take this is a parallel combination of this one, and you take the lower plot here. which is GO, 0, right? And this one, this is open. Then this is the same as G2. This is the G2. Is GO F infinity and GI F infinity is this one. You take the larger one and you take a smaller one. That is a GOF. Okay? So this is the basic way of analyzing filter stage. Don't go to the derivation of all the transfer functions. That won't provide anything to you. Okay? You have a bunch of equations. That's it. Okay? So follow this graphical approach. It provides some insight. Okay? And it also provides some insight how to design filter later on. Right? So we stop here. Okay? Then next time, because we know this characteristic, GO, F0. Always it looks like this. Then we know this, right? Input impedance of downstream converter. Then maybe we come up with something similar to previous case to have some conclusion about the stability of integrated system in filter stage and downstream converter. Okay? So this Thursday, we have class. But next Tuesday, we'll skip that class and the makeup class can be arranged, okay? If we have to, right? All right, okay, thank you.